I think you can see my screen, right?
Yeah, we can see it if you just want to turn on your like present, yeah, to make it bigger. Perfect.
Thank you, Kyla. Hello, everyone. My name is Amir, and I'm working at Environment Canada. My presentation today is about EC Wetland Predictive Mapping Model Project. Our work specifically is focused on operational wetland classification using multi-sensor and multi-temporal remote sensing data. Part of our research in geomatics lab at Science and Technology Division at Environment Canada and Environment and Climate Change Canada was focused on operational wetland monitoring using remote sensing data and machine learning. Recently, we are trying to scale up our workflow using local and commercial cloud-based platforms, such as our in-house data cube and high-performance computing environment, and some commercial platforms like Google Earth Engine. Currently, workflow that can successfully perform large-scale nationwide wetland type classification with acceptable accuracy. The previous attempts are either too expensive to repeat or inconsistent in terms of input data and classification methods, or if repeatable, accuracy is not acceptable. We noticed that accuracies are not acceptable for end users. Example of that, recently published Canadian Wetland Inventory. Here I want to highlight the components of one operational wetland monitoring using remote sensing and machine learning, and some problems that comes with those components. The first thing that we need for operational monitoring is input data. We usually use remote sensing. That remote sensing data could be either spaceborne or airborne. Spaceborne, we have different sensors, satellites. The main ones that we use are radar and optical. Radar has this problem of consistent incident angle coverage. Here I have shown one example in this image. What you see on your left, we try to get complete coverage for some big area in BC interior. And you see the footprints of radar coverage ascending and descending acquisition in 2018 and 19 in yellow, in orange and red. Using that data, we try to extract surface water over these AOIs, over the area we had coverage. And now you see that on your left, you see the surface water products that we created using that radar data. What we noticed is that first of all, we didn't have full coverage because there's always conflict between different users, and sometimes we lost some acquisitions. Another point is that because for a given area, we didn't get consistent incident angle, we noticed that we cannot use those products for change detection, because in a given area, we might want with different incident angles, and the products were not consistent. So we couldn't use that for good change detection. For optical data, I should mention that radar can see through clouds. This is the advantage of radar. But then the problem is we need to have consistent incident angle coverage. For optical data, we have cloud issue because it can see the cloud. Here I have shown one example of one area in Peace Williston watershed in BC, and we wanted to see what is the coverage, for example, in May. And you see that we didn't get full coverage. We got 65% coverage in this period of time. Then for later in the season, for example, over the peak of the growing season, we also didn't get good coverage. So this is the problem that we have with optical data. For airborne platform, UAV could be one example of that. The main problem is that it's a scaling up and coverage in big areas. This here I have shown a 3 UAV survey we have done in shallow water study site at Bay of Quinte in Ontario, which is 3 hours from our office in Ottawa. So we did 3 survey in 2018, and you see that this area is vegetated later in the season. This area is about 2 square kilometers, and for each of these surveys, we spent 1 day, 2-3 of us went to the field and did this coverage. So it shows that for larger scale coverage, it would be really difficult. But the resolution of this type of data is much better than the ones I showed you earlier. For example, radar optical, we get order of 10 meters. For high resolution imagery, we might get up to 1 meter, but with platforms like UAV, we can go on the centimeter level in terms of pixel spacing. So one important thing to consider here is that in multi-sensor analysis, if we create some products, usually the resolution of final products, if we use multi-sensor data, will be based on coarser resolution imagery. Another component of one operational wetland monitoring workflow is field data. We use this field data for training machine learning. I have highlighted 3 problems that we have here. The first one is that usually we don't have expertise or resources to take advantage of field data collected by the groups from other disciplines. This is very important point because we work with CWS colleagues, and they are people there that they have very good background in biology. They go to the field, they collect training points, but usually translating those training points to something that is useful for remote sensing sometimes is challenging. Among all the data or platforms that I've seen some field data, here I have highlighted one. I took the screenshot of Williston Wetland Explorer 2 that is created, I think DEPA is the one who put this data together. This is one of the few sources that I saw that the training data here is appropriately labeled and it's ready to use. We can go just to this platform and then get the shapefile, and then we have all information we need to use this for. And specifically the labels, how they labeled, and then categories of wetland, how they classify those is very user-friendly and it's useful for us. Another point is the spatial accuracy of field data. Imagine we want to use, for example, some collected field data in this site that is covered by UAV data, and we want to classify this UAV imagery. The resolution of this imagery is about 10 centimeters. If you have collected a point or labeled a point, and you took the coordinates of that with GPS, that is could be, for example, your cell phone with 5-meter accuracy, that coordinates does not have the accuracy we need to classify this high resolution imagery. This is another point that needs to be considered. And another one is different classification system. Again, here, these training data that you see are labeled are based on, for example, BC classification system, and that could be different from a Canadian wetland classification system. And then if you want to do a Canadian-wide classification, you should pick the classification that is applicable to all Canada. And then this means that labels here might be something else in the other classification system. Also, one component of this operational wetland monitoring workflow is machine learning algorithms. There are different families of machine learning algorithms. Here I put a classifiers and argue that whether we need all of them, and has ranked them all based on their performance. In remote sensing in community, random forest is one of the most popular classification algorithms that we use. There are multiple reasons for that. For example, in this classification algorithm, we have control over the strengths and diversity of the models that we create. This method is ensemble learning approach, which is very powerful and can extract information efficiently. And also, it's kind of advanced thresholding algorithm. It's very smart and it's decision-based algorithm, which doesn't have too many input variables. Another one that is very efficient, but not as popular as random forest, for example, is support vector machine. This is also efficient algorithm that maps the data to a high dimensional feature space. And with that, we can find the safe decision boundaries and separate our data. But the problem with this algorithm is that it's hard to tune the model and it's not straightforward. It has too many, it has inputs that should be tuned. Unlike the other two algorithms that splits the data, here I have highlighted another popular method in remote sensing that takes advantage of texture information. In random forest and support vector machine, those algorithms does not take advantage of texture information. But in family of neurons, for example, in this case, convolution neural network, it's algorithm that use texture information. This algorithm is useful for high resolution imagery, but on the other hand, it needs lots of training data, which in some cases is expensive to prepare. Now, after knowing these components of operational workflow for wetland classification, I and train the models and efficient machine learning algorithm. Let's say we know we have all these components. Machine learning, for remote sensing data for large scale classification is it's large volume of data, and to process that with machine learning algorithms, we need lots of computational power. So we need to have this data organized in a cloud somewhere. Now these days we can use a cloud-based platform, and then with some high performance computing environment, we can process those images and classify them, for example. There are a few platforms that are now available and have some freely available data. Google Earth Engine or the Google Cloud Platform, it's some of these images also available in Amazon Web Services. There's another European platform, CreoDiaz, that uses Sentinel Hub and have some of the imagery there. Or we can download these data or any type of data that we have put it in our local data cubes and then process them with our computers or our local HPC. Another component that is important is hosting training data somewhere, because there will be for larger scale class training data, and then that should be in the same format, standard format, and we should save them properly somewhere. Sometimes we have some other resources for can use to extract training points, but we should have a good protocol or a standard protocol to have consistency in extracting that data. So these two platforms should be able to talk to each other. And then after that, at the end, we will have our wetland type classification products. Imagine now we have decided about these components. For example, we know which sensor we want to use. For example, for radar and optical, now Sentinel-1 and Sentinel-2 that are both 10-meter resolution are freely available in most of the big data platform or a cloud-based platform. They have consistent acquisition and then freely available. So let's say we are using these plus some reliable DEM data. And now we imagine we have asked our colleagues and we got the training data that we use. Those training data should be high quality data. And then for machine learning, let's say we are using random forest, which is efficient and easy to use. for classification problems like wetland classification, but it comes with some limitation. And for those limitations, let's assume that we are using best practice to reduce those. So we can use this algorithm consistently multiple times to create products. Now, the question is there any way to find out if the generated classification results are consistent from year to year? This is important point because the objective of the or for in a design of operational workflow, our objective is to do or classify, generate classification results that can be used for change detection. If these results have inconsistency and we cannot use them for change detection, we notice that users do not like those kind of products. To achieve this, input data and the classifiers we should use consistent input data and the same classifiers. But with all this, now the question is that what is the criteria for the systems? How do we know that if we create some results, they are consistent? To answer this question, which is an important question, we did a test. We did some research. This test case that I showed you is we picked our study site in Bay of Quinte. And in that study site, we have sites that have includes water, shallow water, marsh, swamp, and forest. And we collected multiple imagery in 2016 from different sensors: Landsat, which is optical, RadarSat-2 data, which is radar C-band, TerSAR-X, which is radar X-band. And then we have these multi-temporal in spring, summer, fall. These, when we stacked all these data together, we end up having 427 predictor variables or imagery. These imagery are either directly came from the sensors, either they are direct polarization backscatter values or a reflectance value for optical, or the derivatives of those could be, for example, different indices from optical data, different decompositions of radar backscatter. And then when we put all these data together, then we try to select the most important one. There are ways to do that. Random Forest has importance measures, so we can see what are the importance predictor variable ranked, or there are more efficient, other methods that are more efficient than Random Forest importance measure. But we did that, so we picked the 4 most important variable and did the classification, 5 most important variables and did the classification and plotted the accuracy of each classification with different variables. You see the x-axis is the number of important variables, for example, 10, 20, 30, 40. And then with each stack of data, we repeated the classification with the same training points, and then we assessed the accuracy. You see this is an interesting plot because it shows that the accuracy after 20 predictor variable or after stacking 20 most important predictor variable, it also gets to a plateau, which is a good news because it says that we don't need to include all those images from different sensors. So as long as we pick those important variables, it seems that we get a plateau, and this plateau is that consistency that we are talking about. For a given classification problem, for example, in this study site, if we do a classification this year, we reach to this plateau. If we do a classification next year and we are in this region of accuracy, then that means we can compare the results, and probably that would be a sign, more likely would be a sign of change rather than sign of detecting inconsistency of input data. There are a few points that I want to highlight, which is summary of this test that we did over this site. One is that for a given classification problem, accuracies have a plateau. This is, as I discussed, is an important point because that is somehow how we can quantify. We reach to a level that it's good enough, and then if we cannot get better than that. For optical radar, and these results showed us that the optical radar and DEM provides complementary information. So probably if we get combination of these, in a combination of images from these predictor, from these sensors, we end up having complete information to reach to this plateau. We can reduce, another thing we noticed that there are different reduction algorithms to find out the best predictor variables, but we noticed that we can reduce the number of variables to minimum possible with maximum accuracy. So with 15 to 20 in this case, for example, we can reach to that plateau, and we know what are those predictor variables and coming from which sensor. Another interesting point was that with a few multi-sensor, multi-temporal predictor variable, classification accuracy can reach to this plateau. When we check those 20 most important predictor variables, we saw that it's coming from optical data, optical sensor, radar sensor, and DEM, and they are multi-temporal. So which means if we pick Sentinel-1 and Sentinel-2 that are freely available, they're radar and optical, and then we have some reliable elevation information, then probably that could be a good data set to begin with and start to classify at larger scale. Now, important point is that now that we can reduce the number of predictor variables to a few, we know what are those and what sensors could be potentially. Now the question is that what if we miss some of these images? For example, I showed you that the problem with optical data is that we have cloud issue, right? What if, for example, early season optical data is important for our classification problem, and we miss that because of cloud? So it would affect our accuracy. The question is this, if that happens, whether can we reach to this plateau? To answer this question, we did some tests. Here you see one very nice wetland complex in this Williston Basin in BC. Here I have showed the location of that approximately on your left, and on your right you see the zooming, and that this is high resolution optical data. We did classification using multi-sensor, multi-temporal, Sentinel-1 and Sentinel-2 early late season imagery, and this is the results of classification, and these are the classes. You can even visually see that this classification is so correlated with optical data. You can clearly see that, for example, if you have bog here, you can clearly see that is distinct in this image. If we have marsh, you can see that this water body is surrounded by marsh. These are the features that even you can see visually, and machine learning can capture those as well. But as a reference, I also put radar data here. And you can see that this radar data is not as much correlated as this optical data is. And you see, so that means maybe if we lose radar data, it's fine, but if we lose optical data, it's not fine at all. We don't know, or we don't know how much this would affect, but this is something we should be able to quantify. The radar data I can see through cloud, then we always have radar data, but this is not the case for optical data. To investigate this, we used a analysis like game theory. In game theory, so to just give you an idea how we did that, so we can consider classification as a game, and input image, category of input imagery from different different sensors, we can consider them as group of players. Then the outcome of the game could be accuracies. If we consider something like this, we can use analysis like game theory and evaluate the contribution of each group of player to the outcome of a game, in this case, accuracies. We were lucky that our colleagues in CWS provided us with very nice reference classification in Vigean National Wildlife Area in BC. So this this reference classification is based on very good field work. And then we tried to use this reference classification. We extracted some training points, and then we created classification wetland, non-wetland water. And you see it's a pretty good match. We did this using early, late Sentinel-1 and 2. Because we had reference classification, we were able to do reliable accuracy assessment. This is an important point. Because we were able to do reliable accuracy assessment, so we could have a good outcome of the game. And then with that, we applied this game theory analysis, and then under two different scenarios. The first scenario, we considered wetland, non-wetland water classes, and then the players were three groups: optical data, radar data, elevation data. Here you see that, and these numbers that you see are contribution of either overall accuracy or per class accuracy to the total accuracy of the classification. You clearly see here that the contribution of optical data is higher than radar data and relatively high, a little bit higher than elevation data. This is for wetland, non-wetland water scenario. But we did also, and then it's a second scenario. We used our players in this case are early optical data, late season optical data, early radar, late radar, and elevation with detail classes: bog, fen, swamp, forest, water. And for here, now you see the contribution of each input data to the classification accuracy. The interesting point here is that either early optical or late imagery contributes way more when we compare it to radar data or even elevation, although elevation contribution is relatively high. So we see that for each class, we have relatively, about 20%, in some cases less, for early optical or late optical. And for radar, this contribution is way lower. What it says is that if we lose optical data because of cloud, could be an issue, because we cannot reach that plateau. And that means we cannot create consistent results. And this is not good. To see how we can address this problem, and this is a good example of that. I showed you that in Williston, we wanted to have full coverage of early, late season optical imagery, and we saw that we don't have full coverage because of cloud. And then, so one of our colleagues were able to give us the products like this. So these are the product mosaics of or composite mosaics of optical data, and they created these mosaics for spring, summer, fall. And how it works, they base 1 year, for example, 2018 or 19, and then that they get whatever they have in that year, free cloud images. And then after that, they try to fill in with the same time imagery from ±1 year. But there's complicated algorithm behind this, because they can weight different things and then somehow making sure or trying to make it better, to make better mosaics. And you see here, they were able to create spring, summer, fall mosaics for us. And then, although these mosaics might be a little bit lower quality compared to the time that we have no cloud condition, but I think you see that from our analysis, optical data contribution is high. So we need to have products like this to be able to reach to that plateau. Here we did a classification over that study site in Williston with 2 different platforms. On the right, you see the classification using Google Earth Engine, using early, late Sentinel-1 and 2 in 2019, plus DEM. We also included DEM data. We got the training points from the training points that DeepA gave us, and then this is the classification. And we also tried to do the same classification using those mosaics, summer, spring, summer, fall. But because these mosaics does not exist in Google Earth Earth Engine, we created, or my colleagues created that, and then we pushed that to our in-house data queue. And then in our in-house data queue, we also added all temporal Sentinel-1 images in 2019, and we repeated the classification. But this platform is completely different. But we see that in our data queue at that time, we didn't have DEM, so we didn't include. That's why in DEM, in the analysis, that's why you see this confusion in upland, which can be easily removed if we include slope, for example, in the stack of data. But over the wetland, which is flat area, we see that we get convergence between the two results, which is a good news, because we should make sure that if we use different platforms, the results converge. We also compare the results with some seasonal time series. This is done with a algorithm we call it a functional PCA. These results are more reliable results because it uses time series of radar data that are more robust. So when we see a patch here in that analysis, it's a good sign because these are more reliable, and when it's matched with the classification, then we are confident that our classification is good. Here is the workflow that we have for our classification. And if for a straightforward cases, we use Google Earth Engine. And then when we don't have cloud issue, but when we need to create those optical mosaics, we use our in-house data queue plus our in-house HPC. When we assess the accuracies, it will be checked by our colleagues, and then we create final results. Here is the example of classification using Google Earth Engine over Columbia Valley. Our colleagues in CWS provided these training points over these 4 study sites, and then we did the classification, and using these training points from these 4 study sites, we extended the classification to entire Columbia Valley. The last, I have 3 more slides left. The last important point that I want to highlight is about field data. Field data and field data transferability. It's very expensive to acquire, to go and collect a good quality training data. And to repeat that each year, it's more expensive. So now we are working on, in our lab, we are working to see if we can develop some algorithms to check the transferability of field data using remote sensing data. One of our colleagues from Statistics Canada helped us to develop an algorithm using functional principal component analysis. In this analysis, we can get the training data, time series of some training data. We create a feature engine, and then we run all seasonal time series of pixels through this feature engine and come up with some scores. Here I can show you some of the results. So in Bay of Quinte, you remember I showed UAV survey over this shallow water in slides earlier. This is the same study site. We have in this study site, we have that shallow water study site. We have some area with marsh, forest, swamp, and agriculture. We did classification, and we picked the extent of marsh. Here you can see that. And then using this type of analysis and tools like FPCA, we can use the same training points, extract the seasonal time series of those training points for 3 years. We create feature engine and create results like this. What you see in these results, each pixel is kind of representative of the seasonal time series of radar data. And you see that because we use the same feature engine to train this, what the difference you see between years are real differences that is captured by those seasonal time series. And this is important because it's kind of showing the transferability of data through time. I have an example here. So if I zoom in here, you can see that this bright green is shallow water class. I used temporal data from a better radar sensor, that is RadarSat, which has much better noise floor. And then with that temporal data set, I was able to extract permanent water mass. These white extent that you see, these are permanent water mass that are created using 6 or 7 radar 2 imagery. And when we do this FPC analysis, we see that the extent of shallow water in 2018 is this much. We know that 2018 was normal year, so the extent is correct. It is captured by RadarSat-2 and also with a time series of an FPC analysis using Sentinel-1. In 2017, we know that was flooded year. The extent of shallow water was decreased. We can capture it with RadarSat-2 as well as Sentinel-2, and these extent matches. So having this type of analysis, just using remote sensing data, we can capture the extent of shallow water. Now, imagine if you introduce training points over this area, over entire area is shallow water. This training data is valid for 2018, but in some areas not valid for 2017. This is something that we are trying to see if we can do with this type of tools and analysis. It could be easy to do it for specific classes, but might not be easy to do it for other classes. But it's something important because it will help us to save money and not repeat, keep going to field. And my last slide, which is transition slides to the next presentation by my colleagues, Erin Roberts, is about the point that it's important how we label the collected field data. Erin gave us some training data or a reference classification using fieldwork, which you can see on your left. And then we used those to extract training points and did the classification. You see a good match between classification and field data. And then there was another, it seems, different interpretation. Erin will discuss about that more. And then they gave us another field classification, which we use as a reference. And then we extract training points, and then we end up having relatively the same results based on this new training data set. So just to highlight that how we interpret the field data and how the field data is labeled is important, and it's important to have a same protocol or standard way of collecting training data. And with that, if we use, we can get more consistent results. Thank you.
Thanks, Amir. That was great. Cindy, do we have time for questions now? I guess if anyone has questions, they can put them in the chat box or turn on your mic to ask them. And if not, it was a lot to digest. We will move on and then have time at the end after the rest of the presentations. I do have one question for you, Amir. In your second last slide where you showed the 2017 and the 2018 data, and you mentioned that the 2017 data, was it the points that weren't valid, or it just like didn't fit into the classification? And do you have any idea what the reasons would be that that wasn't valid? Like,
well, I think if you're referring, so the extent, because the water level was high in 2017, so the extent of shallow water was lower. And shallow water, when we say shallow water, is where at the early season we have water, and then later in the season, that's where the vegetation gets dense. So that bright green was the area that was vegetated. So that because of low level of water, that happened. And we exactly know what exists there. In that site, we have lily pads, we have wild rice that are sensitive to water level. So in 2017, because water level was high, so it was not fully vegetated. But in 2018, the water level was low, and then that was completely vegetated. And that was captured by these two methods. And then that somehow shows that, okay, if you consider the whole site as a shallow water in 1 year, for example, you go to the field, you collect training points, training points, first of all, you should go twice, at least three times in that season, because otherwise you cannot see the entire story. But if you go and collect training points for shallow water in 2018, that doesn't mean can be used that entire training points can be used for 2017, because 2017 has less extent of shallow water class.
Right. So does your the field training points, do you have to match the imagery that you use to process that area to be in the same year of when the field points were collected?
Yeah, and that match is for, in this case, because we are using multi-temporal imagery, it's for the entire season, right? So that match, if I wanted to only classify early season imagery, I should assume water over the entire shallow water class. So that class would be water for me if I just use, because that image shows water in that. But because shallow water is the definition, there's water at the beginning, but vegetated later in the season, and I consider the whole season using multi-temporal, that should be tagged as a shallow water. And yes, it should match the imagery, but it depends what is the analysis. So if you are using time series, you should consider everything during that for that time series.
Okay. So in an ideal world, would we only collect field verification points at the lowest water level then?
Lowest water level?
Because then you would have like the most potential, at least in the shallow open water scenario.
Well, but that would be only applicable for just 1 year, not the other year, right? Yes, but your question is lowest water for a given season.
Right.
Yes.
Well, I don't see any other questions in the chat box, so I guess we'll move on to Erin. So Erin completed her undergraduate degree at the University of Waterloo and is an interdisciplinary environment and in the interdisciplinary environment and business program. She has since completed her Master's of Science in Ecological Restoration from BCIT and SFU. For her graduate research, she investigated aspects of a former log sort and estuary restoration site. She has 10 years of experience across both public and private sectors in Alberta and British Columbia in a variety of field, policy, and project management-based roles. Erin has been with the Canadian Wildlife Service in BC for 4 years, helping to manage and restore natural wildlife areas. More recently, she has focused on ways to enhance wetland science, conservation, and stewardship in BC, and has also helped us develop the field verification points that we worked on this year, part of the wetlands workforce. So without further ado, Erin, if you want to share your screen.
All right, I'm just queuing it up over here. Thanks, Carla, for that kind introduction. That should work.
Yeah.
Okay. Thanks. Thanks very much for having me here today. Typically, I live and work in the Coast Salish territories of Squamish, Musqueam, and Tsleil-Waututh nations. But today I'm joining you from the north central Vancouver Island in Wew'wakam, Wew'wakai, and Hamakako nations. I am a wetland specialist with CWS, and while I've been with protected areas in CWS for 4 years, I'm brand new to the wetland specialist position, but I'm excited to dive into the deep end of wetland classification with you all today. So just to give you an overview of what we're going to be talking about, I'll kind of briefly introduce the National Wetland Inventory and how my work intersects with the machine learning programs that Amir is working on. We'll talk about the need to crosswalk and specifically the protocol that we'll be proposing to use to translate wetlands classified from the British Columbia system to the Canadian system. And I'll spend most of the time today going over case examples of specific site association communities and how they translate over and where there's sort of inconsistencies and kind of all sorts of fun classification instances. And then we'll go over some next steps. I included this photo here because it's from our wetland classification system up in Widgeon, and it sort of highlights some of the interesting differences in classification. So you can see that there's an open area in here, which somebody could qualify as shallow open water. But it is part of that typical kind of pattern bend ecosystem that you see. And so another way to interpret this is a open water pool within a larger fen complex. And so one might just draw the boundary of the fen around the entire shrubby fen community and not delineate shallow water as these tiny little ponds within it. And then if you look at the vegetation in the shrubby system surrounding it, its vegetation is very indicative of both fen and swamp type communities. And so unless you dug a soil pit and confirmed that there was 40 centimeters of peat and organic matter, it would be fair to qualify this as a fen or a swamp, and also a fen or a shallow water or a swamp. And so there's just many ways to cut the pie, and we're going to dive into that today. And so why we need to crosswalk. So it's important to all be speaking the same language when it comes to national wetland inventory, and this helps ensure consistency in the reference and training data across the country, which is why we've chosen to use the Canadian Wetland Classification System for this purpose. Most of the site associations in the BC book, Land Management Handbook 52, translate quite simply over into the Canadian system, but there are a few oddballs and a few ones that require further interpretation and analysis to kind of determine what they would move over into. And mostly in this instance, we're talking about peatland and sort of those swampy riparian classifications. Now, just wanted to spend a moment acknowledging that there are lots of different perspectives and ways you can kind of cut the pie and analyze the situation, and all of those perspectives are valid. To the person on the left-hand side of the screen, from their perspective, they can really see 4 sticks, and to the person on the right-hand side, they really can see 3, and those are valid and founded in reason and logic. And so what we're trying to do here is to bridge the communication gap and to figure out where that disconnect lies. And so when somebody says 4 over here, we know that that means 3 to this person, and we can kind of figure out the formula to translate things over. And so the fundamental difference in approach, and you can kind of like read this straight from the textbooks yourselves if you like, but wetlands at BC, the focus is really on vegetation and site features to identify the different classes. And the Canadian Wetland Classification System has an emphasis on what's called the overall genetic origin of the wetland. And so that means basically how it was formed and developed. So the Canadian Wetland Classification System focuses a lot on climate, like precipitation and temperature, wind and insulation, as well as hydrology, so internal and external drainage, chemistry of both water and soils, and geomorphology to determine what the classes are. Of course, there's aspects of both vegetation and genetic origin in each other, but there's just a tendency and a focus towards these different kind of ways of looking at things. As I said before, both systems have merit, and so it sort of just depends on what question you're asking. If you're looking at certain plant species, presence or absence, or a biodiversity index, you might find more benefit in the wetlands of BC. You actually probably would, because it would actually tell you more about the specific vegetation that are in each class. But if you're asking questions about formation or carbon storage or hydrology processes, the Canadian system would be better suited to your mission. So let's take a look at the crosswalking protocol. And so there'll be some sort of source data available, and that might be TEM data or sensitive ecosystem inventory data, or just vegetation polygons that have been delineated and identified. And then what I'm working on is developing a crosswalking tool to tell you that a WBO1 equals a what in the Canadian system. And we're not trying to put things into boxes preemptively. And so where there is more than one possibility, we'll just identify that it could be a bog or a fen or a swamp or whatever. And then in order to qualify this data more, we're asking folks to assign confidence levels. And so kind of the gold standard, the highest of the high, would be having a soil profile within the polygon that you're looking at to confirm specifically right then and there what it is. And that's unrealistic in a lot of senses, but that would be kind of considered the top of the top data. Most of our data is going to fall within the high or medium confidence levels, which is also great and high quality data, but we just sort of want to distinguish what we have absolute certainty on for a point in time versus things that we are making inferences on or making our best guess based on available information. And so then there'll also be some sort of guidance document that will kind of provide folks some information on how to specifically walk through these processes and what the end schema will look like. Okay, so I want to spend a little bit more time talking about the Canadian system because I presume that most people in this workshop are more familiar with the Wetlands of British Columbia book that you can see on the right, but we need to know what we're moving system things into. And so it's important to frame our minds around the Canadian system. So as a general rule, the guidance will advise to start with the soils wherever possible. Obviously, this isn't possible if you're doing desktop delineation from orthophotos or if you're making interpretations from a satellite machine learning program, but still, it's important to use whatever information is available for you. If there are no soils, then it would be appropriate to move on to hydrology and water chemistry next, and then focusing on vegetation at the very end. And so the main difference in the Canadian system is mineral wetlands versus organic wetlands. So if there's more than 40 centimeters of organic, generally you're in an organic wetland. If that 40 centimeters of organic consists of peat, then you're in a peat wetland, which is what we commonly know as bog and fens. On the other side of the equation, we have the mineral wetlands, which are largely dictated by hydrology and vegetation structure. Swamps would be wooded or forested. Marshes are those graminoid systems, and shallow open waters are more aquatic. So it's important to also note, especially on the mineral side, that there are non-wetland counterparts to each of these systems, which we have to be mindful of. A swamp could just as well be a forest or just shrubland. A marsh could be a meadow, and a shallow open water could be a lake. And particularly on the mineral side, the vegetation that exists within these communities is very tolerant a lot of the time of a wide range of conditions. And so looking at vegetation presence alone, like willows or dogwoods, alders or birch or fern, are not enough to indicate wetland class, because you also need the soils and the hydrology. Okay, so in the Canadian system, what the difference is between a bog and a fen. And so we know that both bog and fens have more than 40 centimeters of peat, and that's a fairly clear delineated threshold. The difference then comes from the nature of the ombotrophic nature of a bog. And so that means that the water inputs are from precipitation, fog, and snowmelt. You can see that because of that water influence, it's nutrient poor, because there's no surface or groundwater influence, and thus it's acidic. And so we have a fairly tight pH range here for bogs of 4.8. And then of course there's the classic vegetation communities that exist because of the soils and because of the hydraulic indicators. And so we have the peat mosses and the stunted shrubs and trees. Going over to the fen side, we have the same amount of peat, but there is that surface and groundwater movement, which is what drives all of the other things. And so because of the surface water and groundwater movement, the water table is at or a bit above or below the surface. And then because of that influence, the nutrients can be poor, medium, or rich. And so a poor fen, and so just like a little bit of surface or groundwater influence, doesn't really change the pH that much. And their range goes up to 5.5. And the vegetation, as a result, is fairly similar to bogs because you'll still have the same peat and stunted trees and shrubs. But because of the surface and groundwater influence, it's technically a fen, even though if you just walk into it vegetatively, it'll look the same as a bog. With more nutrients and more surface and groundwater influence, the sedges and the brown mosses start to appear and the pH range goes up. And then if there's even more surface and groundwater influence, more nutrients, then you'll have a rich fen, which might include things like birch and willow and tamarack, provided that it's not too wet. And so the difference is fairly clear here. And so in the Wetlands of BC book, bogs can go up to 5.5 pH, and you can see that that includes those nutrient poor fens, and a fen would be greater than 5, a pH of greater than 5. And so there's a little bit of kind of like a wiggle room in there, which is why we have these differences of classifications. So I'm going to give you some examples. And so the WB06 bog within the Wetlands of BC book, we're kind of going to be detectives and look for clues within just what like everybody would see as a wetland technician out in the field. The definition here is a common bog / poor fen site association. That's a first clue. And then it talks about groundwater inflow seeps, talks about sedges, which would be more nutrient availability than a straight up bog. And then it talks about the water table being high throughout the season. And so these are all clues that we're actually in a fen. And then if you go down into the comment section, you can see that the authors will actually agree and acknowledge with this point. And so WB06 is transitional to fens and would be considered a fen under some definitions of wetland classes. But due to the many floristic similarities to true bogs, it's placed within a bog for this guide. So it's a completely valid point, but we're just teasing out the differences, and we'll be fairly confident if it's a WB06 that in the Canadian system, this is just a fen. Now, going down to WF04, and so this is a Barclays Willow Water Sedge Glomoras fen for the BC system. Right away at the top, you can see that it's kind of coded as a fen / swamp. So it could be either, even in the BC books kind of description. And then we see that there's the surface and groundwater influence. That what I've highlighted here at the bottom is the soil properties. And so it talks about peat being often shallow due to low biomass production, but occasionally deep sedge peat deposits are encountered. And so if there was those deep sedge peat deposits that were more than 40 centimeters, it would be a swamp, or sorry, it would be a fen. But if it didn't meet that threshold, then it could be a swamp. And so it really depends. And you wouldn't know for sure unless you had some soil data. And so in this case, if you were a crosswalker looking at the system and you had soil data, you could give it a high, confidence rating and call it whatever made sense based on soil profile. But if you didn't have any soil data on the plot, you would give it a medium or a low classification and give it a best guess. And that is kind of the most accurate that we can be within the Canadian system. On the other side of things, swamps are always a little bit confusing. They can be either organic or mineral soils. The water table is at or below the surface. They're definitely minerogenous. There's a lot of groundwater and surface water influence here. And there is sometimes a lot of organic material, but not always. And of course, we have lots of trees and tall shrub covers and like a nice woody, swampy ecosystem. But in the Canadian system, swamps include like wetlands with poorly developed hydric mineral soils. And this is where it gets complicated. Because if it's an organic swamp in British Columbia, those transfer quite simply. But if it's a mineral soil that's poorly developed, that still has a lot of water influence, that doesn't have enough time to develop like a lot of organic matter, it could still be a wetland, but it's more complicated. So let's look at some examples. This is the Floodplain Association 02. And so mountain alder, red oyster dogwood, and lady fern, these are all kind of those facultative vegetation species that can occur just in a forest well away from a lot of water influence, but they can also be right in the middle of a swamp. And so here they can be found under low gradient floodplains or loamy and fine texture soils with moderate duration of flooding. So there's definitely the hydraulic indicators there. And then the soils can either be humic glacials or cumulus regisols. And so this is where I feel like the language is a little bit tricky to interpret, but the glacials are a hydric soil. And so typically if it's a glacial, then it's going to be a wetland because it has those like typical wetland indicators already in it. But if you have the cumulus regisol, it could have hydric indicators or it could not. But just because it is this type of soil does not mean definitively that it is or is not a wetland. So if I were cross-rocking a system like this, it could be a swamp or a non-wetland. But if you had soil data that indicated that it was more of a glacial, then I would be more confident in saying that it's a swamp. But if it was a regisol, I would not know unless you can actually see the soil profile. If you can see signs of like low oxygen levels, like the redness in the soils and the changing colors, or a little bit more of organic development on top of it, that would indicate prolonged saturated conditions. But this is a tricky one. And so you just don't know unless you have high quality soil data, but you can still make a best guess, and then that's still helpful for training machines, even if it's a lower and medium confidence level. And so there's another one here, FL06, which is a sandbar willow. And so This is typical along very large like river systems, and it occurs within sandy lateral bars, kind of right within the river body itself, but it can also occur around large lakes or wave washed shores. We're probably all fairly familiar with this kind of standard willowy, like low plant diversity thing that you see everywhere. And so they're describing it here as a sandy Kimball-Greco-Sol, and that is not very helpful for determining if it's a hydric soil or not, because it could be, but it also could not be. Generally, I would say that if it's within the ordinary high watermark of the river, it's probably not a wetland because it's probably part of the river system. But you kind of have to look at it a case-by-case basis and make a best decision on the information available. Sand and gravel systems are really difficult, even if you're in the field, to determine if it's a hydric soil or not. And you get like some of leading soil scientists just sort of working through the details and having those conflicts of opinion. And that's part of the process, and it's just a tricky one. But even with that, that's why we have confidence levels to have a similar standard across all crosswalkers and people that are moving things into the Canadian system, and to go from there. Some other ecosystems in the BC book would be like eelgrass beds and mudflats, and those would be shallow open waters for the Canadian system, but they're just sort of grouped under like the estuary classes in the BC book. And most of the estuary classes will translate easily over into like a marsh, but there's a few that are a little bit different. And so just to sort of summarize, some of these things are like quite straightforward and some of them aren't, but generally, if it's a bog, there's a few different options that it could be depending on the hydrology or the amount of peat. If it's a fen, it's not going to be a bog because there's definitely the groundwater influence, but depending on the amount of peat and the vegetation structure, you might have a swamp or a marsh, where BC book qualifies as a fen. Swamps, especially the mineral soil ones, will be probably the most difficult to discern, and they could be non-wetlands. Marshes are quite straightforward. Shallow waters will, again, mostly be shallow open waters, but some of them could be true aquatic systems. And so there's a little bit of nuance around there and how deep the water level can be while still being considered a wetland in the Canadian system. And then the estuaries, again, transfer over to marshes and shallow waters, and the floodplains are quite similar to swamps in the Canadian classes, but many of them will not be wetlands at all. And I haven't figured out the transitional classes yet, so stay tuned on those because those are even more fun. So our next steps with this process are to develop a crosswalking protocol and to circulate it for feedback and to make sure that what we are determining are possible types for each wetland. We have consensus across experts in BC, and to finalize that protocol and to get a lot of data over to Amir to inform his important project. And now this only works for wetlands that are classified to the site association level within the Wetlands of BC book. There could be other types of data in BC, like from SEI data or vegetation polygons or a wide variety of things that might need different crosswalking protocols to determine how different types of data translate into the Canadian system. There's an opportunity to develop field protocols for the Canadian wetland classification system, which is what we've been working with BC, WF, and Kyla on, because there's other types of information that are helpful for machine learning, like the height of the lowest branch and things that are useful for training the satellite machine learning algorithm, but it doesn't necessarily affect the class that it's in. And so that's sort of a sub or side project. And then throughout, it's fairly clear that improved soil field indicators would be helpful for improving the accuracy and confidence levels of determining Canadian wetland classes. And so that will be something that we can investigate further. And I can take any questions. Please note that there's a number 2 in my email. If you omit it, it goes to a different person in Ottawa, and she doesn't appreciate all of the wetland questions. All right, thank you.
Thanks, Erin. That was great. I see one message from Winnie. is there an international wetland classification standard or North American standard to follow? And if not, why, to reconcile the differences between BC and Canada or within North America?
Oh, that's a good question. I don't know of an international standard outside of Ramsar, and that's a fairly broad definition of wetland classes. The Canadian system is definitely the gold standard and what most provinces would use in Canada. And then I did a lot of field work in Alberta earlier on in my career. And so the Alberta wetland classification system would be compliant with the Canadian system. And so it kind of automatically crosswalks. And then if you take some training in Alberta, they rely on a lot of US standards from like the US Corps of Engineering. And that's where you can get more information on what is or is not a hydric soil and specifics around wetland delineation, because as Amir is experiencing, if you're standing in one area that's a shallow open water in one year and a marsh in the next, the boundaries of those things are going to shift year after year. And if you use the US Army Corps methodologies, you can figure out where the boundary is under those systems by having a soil auger test pit at like meter intervals until you stop seeing signs of hydric soil activity. But that's so specific and requires so much field verification that it's probably not appropriate for like our analysis here, but those would be things to consider, how we want to incorporate those into basically just like providing high quality field data to a machine learning program to have a predictive map of approximately where the wetlands are and what classes they are. Did I answer the question?
Yeah, does that answer your question, Winnie? If you have any follow-up, you can turn on your mic maybe. I think that answers it. And then she also asked, are there any benefits for reconciliation? So I think
reconciliation between the BC classification and the Canadian system?
Yeah, between BC and Canada, like the Canadian classification.
Yeah, I think it just helps, make sure that we're all talking about the same thing. And so if somebody is using the Canadian system and just keeps on talking about fens and it's confusing to you in BC, it's probably because the poor fens are poor fens in BC and you would call it a bog in BC. And so I think it's not to say that one is right and one is wrong, but it's just to help people understand and communicate better about the data that we're working with. And so having this kind of translation service crosswalking system, I think just helps improve the understanding of what it is we're talking about.
For sure. And then ST Black asks, are there any plans to update the wetland functions assessment for these Canadian wetland classes?
I'm not sure what the answer to that is, because I haven't worked with functional assessments in the Canadian wetland classes.
Me neither. Is there anyone else that maybe has, or we can bank that for later if anyone thinks of further discussion on it? Jason Straka asked, do you get much or any field data where plots have been done in both BEC, so the biogeoclimatical classification, and the Canadian classification? And is there an easy way to do this? I have also wondered this. Do you have any
yeah, it's a good question. We have a lot of field data that has back data on it, but you wouldn't have the Canadian classifications on it unless you did this crosswalking. And so Environment Canada has several contracts out right now with NGOs and private companies to crosswalk the data into the Canadian system, because it is a different product and a different class, and is working for an Environment Canada project. And so yeah, we're working to do that. And the easy way to do that, I hope, is to have this protocol finalized. And so the protocol would be the lookup table, clear definitions of what we mean by confidence ratings, a schema. And so you have all of your source data, whatever you collected, and then a few columns that would be the Canadian classification system, class and confidence level and date collected, and a few other things. And then a little bit of a guidance protocol to walk somebody through that. And so it would just take somebody reclassifying kind of polygon by polygon what they think things are.
Awesome, thanks. Rebecca, one of our field techs, also asked a great question, but I think Rebecca, you have multiple people in there, so we'll save that till the end, and maybe we can move on to Bing's presentation first and come back to that. So Dr. Bing Liu is an assistant professor in the Department of Geography at Simon Fraser University, and his research focuses on monitoring ecosystem features using remote sensing. Bing's group has utilized different types of remote sensing images, including multispectral, hyperspectral, thermal, and LiDAR, acquired by multiple platforms, including satellites, airplanes, and drones, for investigating a range of ecosystem features. These ecosystem features include species composition, plant physiological status, and the impacts of environmental disturbances like wildfires and droughts. His recent research focuses on mapping species composition and marsh recession in the south coast of British Columbia using high spatial resolution satellite imagery, such as WorldView 3 with 30 centimeter resolution, aiming to support the ecosystem management in this area. And 30 centimeter resolution kind of sounds like a dream. So we'll let Bing start his presentation now if you're able to share your screen.
Okay, so can you see my share screen and hear me okay?
Yeah, you look good.
Okay, great. Hello, everyone. Thanks for having me here. My name is Bing Liu. I'm from SFU. I would like to acknowledge SFU is on the unceded and traditional territory of coastal Salish people, including Musqueam, Squamish, Tsleil-Waututh, and others. So today I will talk about two projects I have worked before. One is wetland mapping, and second is species classification. So for the first project, it's kind of similar to the work by the first speaker, Amir. It's similar to using remote sensing to map the different wetland classes. I will also highlight the contributions of using multi-type remote sensing data, including optical, LiDAR, and also radar. So their contribution and importance for the wetland classification. So for my second project, I will discuss how I use high spatial resolution satellite image for the species classification in the BC South Coast. So to support our understanding of species composition, including native and invasive species in the area. And lastly, I will summarize the wetland mapping using remote sensing based on my research experience. Before I talk about the first project, the wetland classification, I would like to quickly introduce remote sensing, just in case our audience have no idea about remote sensing. So basically, remote sensing is taking images on high altitude using the satellites, airplanes, or maybe more recently using drones. Sometimes we call them UAVs. Some advantages of remote sensing. So the image can cover pretty large area, especially the satellites. So using quite a few satellite images, we can easily cover the lower mainland area and maybe the province BC. So using a larger number of satellites, we can cover the entire country. And because remote sensing data can be acquired repetitively, so we can monitor the wetlands or other ground surface changes, let's say every day, every week, month, or years. And the remote sensing technology is also very helpful for access the remote areas. That's one advantage for the wetland monitoring, because we know some wetland areas are really difficult to access. And another advantage is the different types imagery with different resolutions available, such as the high spatial resolution, hyperspectral image, or medium spatial resolution, medium spectral resolution. So later I will discuss their contributions. So here shows one example of the Sentinel-2 imagery with 10-meter spatial resolution. That's freely available to the public. So that's a good data source with good spatial resolution for the wetland mapping. So my first project about the wetland classification was conducted in the central Alberta with one consulting firm named Farrer Consulting. So our study area is just west of Edmonton and showed here. So if you have been to this region before, probably you know there are just a huge amount of wetlands in this region with different wetland classes. So if we know the distributions as well as their specific wetland classes, it will be very useful for us for the wetland conservation. So similar to the different wetland classes just discussed by the second speaker. So here I will try to we try to classify wetlands using the Alberta wetland classification system, including the bog, fen, marsh, swamp, and shallow open water. So these are the major 5 classes. So besides the wetland classes, we also classified other land covers such as the developed area, forest, bare soil, and other vegetation classes. So eventually we grouped all these non-wetland classes together. So some photos of different wetland classes shown here. Now I will introduce the different types of remote sensing data we used for the classification. The most important data source is Sentinel-2, that is the optical image. So besides the optical image, we also calculated different secondary products, including different spectral indices, NDVI, sorry. So mainly to highlight different information, such as this map highlights the vegetation information, and this map highlights the water information. So such highlighted information can be very helpful for the wetland classification. And we also collected LiDAR DEM data and produced different secondary products to highlight the terrain information and see how the terrain can influence the wetland classification. We also collected Sentinel-1 image, that is radar. So the one advantage of the radar is, besides it can be collected at night or when it is cloudy. So the radar signal can penetrate into the vegetation canopies and then generate different backscattering signals. So let's say for the bogs, marshes, and swamps, if they have trees or if they don't have trees, and that will be generate different radar backscattering signals. And then we can, that's why we can also use the radar image for the wetland classification, basically because the different vegetation covers. So now I will introduce our research method, mainly including 2 components, the object-based imagery analysis, OBIA, and then the random forest classification. The first step is the image segmentation. So basically, we want to segment the image into different polygons or objects that represent different wetlands or other land covers, such as forest object, marsh object, or water body object. And then we selected training sample using these polygons, such as shown here. So the highlighted polygons represent the samples we collected in the field or using the remote sensing image. And then we used these training samples to train a random forest classification. So since this model was also used by the first speaker, Emma. So this is pretty popular and also robust classification model. We used the training samples to train this model, and then this model was applied to classify all the other objects. So such as these other objects that are not highlighted. So these are unclassified objects, so in the field, but can be classified by this random forest model. Now I will show our classification results and show here. So these different colors represent different wetland classes, and the non-wetland, such as farmlands, the building areas were just shown in this image. So from this classification results, we can clearly see the distributions of the wetlands and the whole, all the different distributions of different specific wetland classes. So such information will be helpful for the future wetland conservation and management. So if we can, using a multi-temporal image, such as images collected 10 years ago, 20 years ago, or maybe 30 years ago, and then we can monitor the temporal variations, such as the wetland loss or wetland degradation in the past 10 or 30 years using such classification results. Okay, so that's the classification map. Here, I would like to talk about the important features for the classification. So one advantage of the redwood forest classification model is it can evaluate the contribution or the importance of different variables in the model, such as the image, the radar, LiDAR, optical, or the vegetation indices. So here I show the top 10 important features for our classification work. So here the 5, 1, 2, 3, 8, and 10. So they are all the topographic variables, the probability of depression, the TPI average, or TPI textural average. So these 5 are all the topography or the terrain features. So clearly we can tell the terrain features or the DM data is very, very important for the wetland classification. And the other 5 are all the optical variables that we extracted from the Sentinel-2 data, such as the principal component, the reflectance. So by integrating all these different types variables from the optical data or from the LiDAR DEM data, then we can generate more accurate classification results. So that also reveals for our future research projects, it will be better to test or to integrate different types of remote sensing data and to produce higher classification accuracy. So that's my first project I did before in Alberta. So here I also would like to introduce a second project I am working on right now in southern BC. So this project, we try to classify different species, as we can tell from these 2 photos, or if you have been to the South Coast area. So you clearly, you know, they are mixed species. Some are invasive species, some are native species. So if we can map the distribution of these different species compositions, it will be very helpful for the species management, such as the control of the invasive species. So our study area for this project is mainly the Sturgeon and Robertsback WMAs. So basically our field survey area, including the Sea Island, the Lulu Island, West Ham, the Brunswick, and also the Southern First Nation here. The remote sensing data we use is a commercial WorldView 3 image with 30 centimeter spatial resolution. So for the first project on the wetland classification, we use a 10-meter Sentinel-2 image. So the 10-meter is clearly too coarse or too low for the species classification. So because we know the species are pretty small and they mix with each other. So here we try to collect the highest possible spatial resolution image and then classify the species. So if we zoom in to different areas, we can clearly see the different species patches. And we will try to classify these species patches. Sometimes we found especially some grass species, especially these green ones. So they have similar color, but they are different grass species. In this case, we will merge them together as one class or one object to classify rather than really different species. So our site design and field service, we surveyed 45 transects in our study area. So these transects mainly go from east to west, and then we surveyed every 30 meters to have a new point. And each site point, we collected the species composition. So, and also take photos together the GPS data. So the photo or the species information and the GPS. So these are the 2 most important information for our classification. So using GPS, we can locate the accurate location on the map, and then using our field records, we know which species at each point. So these are information can be used for the classification. So besides the species and also GPS, we also measure the canopy height, also the leaf area index. That's one indicator of the vegetation density. So in the future, we also will try to estimate the density so for different species. This is an ongoing project, and we are still working on that. Here, I'll just show some preliminary results on the imagery segmentation. So this is a similar method I used for the wetland classification, just on different scales. So let's say on higher scale, so we can generate objects represent different wetland classes, such as bogs, fens, marshes, swamps. So here, if we use a much finer or small scale segmentation, and then we can create objects that represent different species patches. So such as some larger species patches or smaller species patches. So on the next step, we will use different machine learning or deep learning methods try to classify these objects into different species classes. So as I just mentioned, some species, they highly mix with each other, especially some grass species. So in this case, we'll just call this mixed species as one class rather than really classify all the specific species. Sometimes that's not, that's just impossible because the 30 centimeter resolution is still not fine enough. Okay, so that's a quick introduction of my second project. Here, I would like to summarize the wetland mapping using remote sensing based on my research experience. So the first important consideration is the imagery spatial resolution. So there are different types available, such as the free medium resolution image. Examples include Sentinel-2 with 10-meter resolution, the Landsat 8, or other Landsat images with 30-meter resolution. So mostly they are okay for the mapping different wetland classes, but they are not great enough for the species classification. And then we can use the commercial high spatial resolution image with meter level accuracy to map the fine scale features, including the species. So I mean, they are commercial images if we want to, let's say, map the species or other wetland features for the entire province. So that will cost lots of funding. So some of the commercial images are still free to the university users, but not to other sectors. So still some limitations there. So the second consideration is the integration of multi-type image. So including optical, LiDAR, radar, and thermal. So thermal image basically reveal the temperature for different land covers. These different types remote sensing data can capture different land cover features, temperature, vegetation cover, vegetation density. So potentially they can all contribute to the wetland or species classification, but it is time consuming to collect all the images available and also computationally challenging, so to process a really large data set. And then it will be valuable to evaluate the contribution or importance of different types, and then using a smart data set to do the classification. The next consideration is imagery segmentation. So which segmentation scale and object size to use. So that will be related to the project purpose, such as for the wetland classification or the species classification, we will need to use different segmentation scales and generate different sizes of objects. However, so we can test different segmentation scales from 1 to 10. So we have the freedom to try large ranges of values. However, it will be very difficult to tell. So which segmentation scale is the optimal scale? So maybe this segmentation scale works well for one wetland class, bogs or fens, but this scale may be too large or too small for other wetland classes or species classes. So we will need to test lots of values to find the optimal number. So the last consideration is the classification model, including machine learning or deep learning. They are different. So these are just groups or different algorithms. And also the training data is super important for the high accurate performance of different models. And in the future, we'll test different machine learning and deep learning models. So using our species training data and see which model can generate the best result. Okay, so lastly, I would like to thank the funding from SFU and especially the CEI project and our collaborators for the CEI, including researchers from DOCS, Southern First Nation, Green Coast, and also 2 divisions from the Environmental Canada and also the Lower Fraser Fishery Alliance. And especially thanks to our field staff as shown here. So it's pretty challenging to do the field survey in the coastal marshes. So they are from DOCS and also from BC Conservation Foundation, BC Wildlife Federation. The funding from the 2 initiatives from the BC province government. Also thanks to Federal Biological Consulting for the first project. Okay, that's my presentation. Maybe I can stay here so to answer your questions. Thanks, everyone.
Thanks, Bing. That was really interesting. I was wondering, the area that you talked about in Alberta, has that classification been like duplicated in any other areas, or was that just one local project there?
Yeah, it's just one local project for research and development.
Gotcha, thanks. I see one question from Jason Straka. He said, how have you looked at how your mixed species polygons might be reflected in vegetation classification systems? If you have mixed species in a 20 by 20 meter plot, that sounds like it could potentially be used to assign that polygon to an ecological community, unfortunately with no soils.
Yes, so that's always one challenge for the species classification. Sometimes the 30 centimeter resolution is still not fine enough to differentiate the species or mixed species, especially different grasses. So in this case, we'll just merge them together as one ecological community, or sometimes we call a functional group. So just use the mixed species as one class in the classification model. Yeah, so does I answer the question?
Yes, thank you.
Mm-hmm. Yeah, so also some further information. Here we use the 30 centimeter by 30 centimeter spatial resolution and try if we can classify different species patches. So in next year, we will try to collect the UAV image or see the drone image that has centimeter level accuracy. So let's say 3 or 5 centimeter. So even higher spatial resolution. And then we'll further test if we can differentiate the specific grass species. That's our future research plan.
Are you going to have to repeat the field verification data, like boots on the ground for the species, to reconcile with the drone imagery, or is it just drone imagery to the 30 centimeter imagery?
So next year, likely we will collect the drone imagery. And there are also free satellite image available with 5 centimeter or 5 meter or 3 meter. So from the planet. So these images are free to the university users. So they are maybe not great enough as the 30 centimeter for the species classification, but they are free. I mean, the World Whale 3 image cost us almost $7,000 for only covering the coastal marsh areas this year. So it's pretty expensive. So next year, we will try to use drone image and also free, but still high spatial resolution image for the classification.
Great, thanks. ST Black asks, is it difficult to distinguish the different types of disturbance?
Different types of disturbance. So Actually, besides the species classification, another topic we will work on using the remote sensing is to monitor marsh recession. So the different disturbances, such as from the wildlife, from the ocean waves. So these are clear disturbances for the marsh recession. So we will try to collect multi-temporal satellite image, such as from 5 years ago, 10 years ago, and then also use the LiDAR data and try to build the DM data for this area, as well as species patches, so such as the front line or the vegetation cover, and see if the vegetation cover may be retreated in the past 5 or 10 years or 20 years. And that could be one indicator of the disturbance and indicator of the marsh recession.
Great, thank you. If there's no other questions, or if people think of them, they can put them in the chat and we'll come back to them after. We will move on to Christina Dienek. She's she's currently pursuing a master's degree at the University of British Columbia in the Okanagan. Her research involves using Earth observation satellite and LiDAR data to predict where wetlands occur in the Okanagan. She has previous experience working as an environmental consultant in BC's interior and as a resource management officer for Parks Canada in the Mountain National Parks. For the past year and a half, she has been living in Nelson, BC, and getting to know ecosystems in the Kootenay region. So Christine, there, yeah, we got your screen, perfect.
Awesome, thanks, Kyla. Okay, I hope everyone is still doing okay. It's 11:15, approaching lunchtime, so just another 15 minutes of attention here. Let's see, you can all see what's going on here. Too many things are up on my screen. Okay. So for the past year and a half, or 2 years actually, I've been doing a real deep dive into the world of remote sensing and wetland mapping. And I really appreciate opportunities like this to talk about my research and share what I've been doing to bring awareness to wetlands. So I want to start with a land acknowledgement. The land on which I conducted my research is the traditional, ancestral, and unceded territory of the Syilx and Okanagan people. And I'd also like to acknowledge that I'm coming to you today from the traditional territory of the Ktunaxa, the Syilx, and the Sinixt people in Nelson, BC. So I'm going to give you a brief overview of Okanagan wetlands. I'm going to share with you my mapping approach that I use for using remote sensing and machine learning. And then I'll show you what some of my model outputs look like. And then we can discuss the applications of this project. So it's important that we start on the same page with the definition of a wetland. And I'd like to bring your attention to these 3 key elements that define a wetland. So water, soils, and vegetation, because this is what our predictive model is anchored on. So all 5 of the wetland classes, as per the Canadian Wetland Classification System, can be found in the Okanagan. In the valley bottom, the most common are marsh, shallow water, and there are a few swamps. And then as you move up in elevation, you start getting some peatlands, so more fens and very rarely bogs. Because the Okanagan is so hot and dry, the peatlands can only exist at these higher elevations because decomposition rates are slower up there. So wetlands are amongst the rarest and most sensitive ecosystems in the Okanagan, but they provide critical habitat for a variety of wildlife, many of which are species at risk. And this estimate of 22,000 per hectare per year reflects the value of ecosystem services provided by wetlands, including flood control, erosion protection, water purification, recreational and habitat uses. And it is estimated that 84% of low elevation wetlands and 93% of river wetlands have been lost, and that 68% of small or shallow wetlands are predicted to be lost in the future due to climate change. So the biggest risks to wetlands in the Okanagan are development, agriculture, and climate change. Okay, so an important first step towards protecting and restoring wetlands is determining the location, the spatial extent, and classification of existing wetlands. And there is an existing wetland inventory for the Okanagan consisting of 6,000 wetlands, and that's what is mapped here. However, the data here were consolidated in 2011, and they're from various field surveys, aerial photo interpretation, and other provincial layers. And so of the 6,000 wetlands that are mapped here, over half remain unclassified, and that prevents further assessment and evaluation for conservation potential. So although it's a good first step, it's likely this database is missing small ephemeral forested wetlands. It's becoming quickly outdated, and there's no temporal component, and it would also be quite labor intensive to replicate. So the availability of LiDAR and open source satellite data have really made it possible to create a more accurate wetland map for the Okanagan. So my research goals are to accurately identify and classify wetlands, to create a replicable model and one that is cost effective, and to improve these existing inventories. So I gathered data from my model from open access satellite, multispectral, and radar data from Sentinel. And this has a 10-meter resolution, spatial resolution, I should say. And I also used LiDAR data that was flown in the Okanagan in 2018 and 2019. And this is now open access as well. I just discovered there's this LiDAR BC open data portal. So you can go on this government website and check to see if LiDAR has been flown in your area and download it. It's super helpful. And I also use some ancillary data such as the Soils Information Finder tool, SIFT, from the province, as well as other layers like land use layers for roads, forestry, and urban areas, as well as the Freshwater Atlas Streams database. So the method of combining multispectral radar and LiDAR data has been proven to be quite useful for wetland mapping, and multiple studies have achieved over 90% accuracy for wetland identification and 80% for classification. And it's just getting better as our technology improves. So from those data sources, I calculated 30 or so different parameters that I thought might be useful for identifying wetlands. And if you recall the definition of a wetland, we're trying to characterize water, soils, and vegetation properties. And optical and radar data are good at determining areas of green vegetation and open water, while LiDAR is really good at getting at characterizing terrain and vegetation morphology. So using the existing database, we then fed all of that into the model to train it and to identify patterns between these parameters and wetland classification. And then the output was a probability map. So these are some of the parameters that we calculated, and don't worry too much about the acronyms here. All I want you to realize is that each parameter that gets fed into the model is picking up on different patterns on the landscape. So this is the same scene that I'll be showing you different layers for. So this first one is NDVI, so the Normalized Difference Vegetation Index. And I calculated the change between early season and late season with the thought that in areas where there was water available, the greenness wouldn't necessarily decline over the season because it would maintain greenness and that water availability. Okay, this one is an example of a radar parameter that was calculated. And radar is quite good at detecting open water and emergent vegetation. This is an example of LiDAR. So this is the standard deviation of ground hits, and it's quite good at identifying flat areas, hummocky areas, and vegetation. See if I can move through this without clicking anything. There we go. And this last one is an example of the ancillary data that I use. So this is degree days above 5 degrees, and that really gets at the climate characteristics to differentiate between classes. So again, going back to the fact that peatlands only exist at higher elevations where it isn't too hot or dry. And this is now a different scene. This is actually Kelowna exists here, and this is the bridge across to West Kelowna. This is topographic position index, and this gives the elevational position of each cell. and it helps to identify low-lying areas, which is where our wetlands are likely to occur. And then the topographic wetness index is calculated from, it takes slope, flow direction, and flow accumulation into account, and it's the relative soil moisture of a particular cell. So the overall accuracy of the model was 84%, and I have here, you can see the user accuracy versus the producer accuracy. Basically, user accuracy is a commission. It takes into account commission error. So it's the probability that a feature classified on the map actually represents that category. So if a wetland class was incorrectly included, this value would drop. Whereas the producer accuracy is an omission error. So it's the probability of a feature being correctly classified. It takes into account all samples that were omitted from this sample class. So if a wetland was missed or not included in the correct class, this value would drop. So the key takeaways from this is that fens were often missed with this low 30% producer accuracy here. But when a fen was predicted, it had high accuracy. So it was very likely that that actually was a fen. Shallow water had the lowest user's accuracy and fairly low producer's accuracy, meaning it was being missed and not always correctly classified. And marshes are the most common wetland class in the Okanagan, and they had high users and producers accuracy. So this is one scene of the model output. You can see pink indicate fens, teal swamps, orange marsh, and blue shallow water. There's actually no shallow waters on this scene. Oh, actually maybe in this corner. And the polygons are from the existing wetland database that was used to train my model. And so you can see in the upland areas, it's doing pretty well, and it's identifying totally new wetland complexes, which is great. However, the problem as you move down into the valley bottom, you get disturbed areas. And so one problem I'm trying to solve right now is to correct for this over prediction in disturbed areas. And the disturbances from urban areas, agriculture, forestry clear cuts, and along roads seems to be the biggest issue. And I've also been having trouble differentiating between swamps and just forested areas. So the next steps is for me are to continue to improve the classification accuracy of the model and to produce a user-friendly output map for secondary studies related to biodiversity and connectivity, land use planning, wetland evaluation, conservation and restoration, and flood mitigation. And so in summary, our objectives with this project feed into the goals for the Okanagan identified by the Okanagan Wetlands Action Plan, as well as local official community plans and other provincial and federal environmental sustainability agendas. So this goal of no net loss by 2025 really requires that we are able to track our wetlands over time and first identify where they're occurring. And there's a lot of funding that's coming out for these nature-based solutions for climate change, where they specifically talk about wetland enhancement as a goal. And again, the first step of which is to identify where wetlands occur on the landscape. So this project would not be possible without the support from my supervisor, Matthew Bourbonnais at UBC Okanagan, and organizations such as the Okanagan Basin Water Board and the Okanagan Collaborative Conservation Program in Kelowna, as well as funding through MyTax. So that's all that I have for you today.
Great, thank you, Christina. Maybe, I don't see any specific questions for you yet, but if the other presenters have had a chance to look at the question from Rebecca. Oh, we had one more question, I think, that was meant for Bing. He asked, have you found some species that are not distinguishable spectrally, such as have similar spectral signatures, and how can you deal with this issue in spectral data?
Yes, so that's a very good question. So yes, we do notice some grass species, they are very similar and they have kind of exactly the same spectral features, very green. So in this case, besides the spectral property we use for the classification, we also use some texture variations, texture variables that can be extracted from the remote sensing image. So basically, we will try to extract as much as more information from the image, spectral, textual information, and to classify different species. However, if, as I mentioned, if some species they just look too similar, and we will just merge them together as one species, not like separately. Thank you.
Thank you, Bing. I wonder if there's any strategic use of the temporal timing of the imagery, like if there's species that flower that are easily confused. Do you target that with what date you're using the imagery from? I think you're still muted, Bing. Or do you just use the imagery from whenever it's available?
Sorry, I missed the question. Can you please?
Yeah, just in like following up to that last questions about species that are not easily distinguishable spectrally, can you target certain timing when they are distinguishable, such as like flowering periods or die-off periods?
Yeah, that's also a very good question. Yes, so different species, they have different phenological features of flowering or maybe the season of sadness. So yes, it is possible to collect multi-season images from the spring, summer, and fall and see if there is a specific time that one species is spectrally or maybe texturally different from other species. Yes, that's a good point. Yeah, that's reader, and we'll try that in the future. Thank you.
I also see more questions for Christina. I knew they would come. Everyone just needed a minute. Jason asks, what was the source or reference for your stats on wetland loss?
Yeah, I'm just pulling that up for him right now. So that one was Harrison and Moore, 2013. That was on a wetland study in the Okanagan, and then the 68% loss due to climate change is Bunnell et al. 2010. So I can put those in the chat for you if you wanted to look at those papers.
Great. Yeah, I think I've seen them. Thank you.
Okay, great.
And then Aaron also asked you a question. Do you want to ask that one yourself, Aaron?
Sure, I'm just moving over to unmute myself. I was just wondering if you or like the broader Okanagan wetland groups have any plans for like collecting new field data to inform your model, and if so, are you going to be delineating things or using a point in the middle, and how would that work?
Yeah, good question. So I think this is a big piece of my accuracy that if I were to collect new training data, I think it would really improve the accuracy of this map. However, with my project, I'm kind of coming to the close and just using what I have available to me. So the existing wetland database as training points. And so I've just selected points randomly within the polygons of that existing wetland database. Yeah.
Thanks.
Great, thanks.
I was also wondering, I don't know, Christina Emir might be able to also help with this, but what is the value to having points versus polygons of similar plant communities delineated? Like for all of our data collection with the wetlands workforce this year, it's all points, but there's like supporting imagery and drone photos. Like, is there value added to having those larger polygons delineated, or is it kind of limited returns on the time to delineate that?
So you have to turn the polygon data back into point data to feed into the model because it's basically it's the stack of all of your 30 parameters, and you have to take a point and kind of figure out what value every single one of those parameters have. So that's how I've been running it, and maybe Amir can speak to this in broader terms.
Well, that's correct. When we use training data, we have the stack of the data, and that we extract the value of each training point over those predicted variable to train model, or do the prediction after training our model. But I think broader base, if we use, this is specific to classification algorithm, since all of us discussed about random forest. Random forest is very biased toward unbalanced training points. And that in that case, if we have rare classes that we have less training points for, then it would be useful to have polygons for those classes so we can densify the number of points and then make them balanced. This unbalanced training points is very big issue for random forest because the way random forest splits the data is using a Gini index, and then that is just based on probabilities. So if only the count of the number is different from one class to another, that will bias the classification. So for that reason, I think polygons of homogeneous patches is preferred to just points, because we can, when it's most likely the training data we use would be unbalanced, and then we can use those to distribute training points over those polygons. And then also, we need to consider about spatial autocorrelation between the points, and that is related to the resolution of input data. When we have polygons, and for example, imagine we use radar data. Radar data, we filter data. If the resolution of radar data is 10 meters, then the filter would be at least the 3 by 3 pixel or 5 by 5, which is we are creating pixels of 50 meter by 50 meter that are correlated, or 25 pixels that are correlated. Then if we have polygons, we can distribute the points in appropriate distance to avoid spatial autocorrelation and things like that.
I guess just to add on to the point versus polygon conversation, just from like a field like data collection and confidence level perspective, point data would give you the highest confidence of what it is that you're delineating, because it would ideally be in the center of the wetland class. And polygons, even with like high quality ortho imager and like careful delineation on like quite zoomed in aerial, you're still making an interpretation, because like that boundary is an estimate and you won't have a very high confidence level of exactly where the boundary is until you do a detailed field assessment. And so while it can be valuable, the polygon data needs to be qualified. And when Amir says a homogeneous wetland, that might mean something different to when Bing says it, because we're sort of talking about marshes more broadly. And so what is homogeneous to one group would not be to another, because like the wetlands in the foreshore of the Fraser have obviously the bulrush and the carex and this and that might not be considered homogeneous under a different kind of research question. So
Great, thanks, Erin. Have Erin and Amir had a chance to look at Rebecca's question, and do either one of you want to take a start at that one?
Well, from remote sensing side prospect, what is the ideal level of ground truthing needed for accuracy and cost effective? I think to do a good job for to accurately classify wetland types, we need to capture the distribution of each class. And that means, for example, if you have a dead swamp, live swamp, that is subclass of one class, but then we need to have enough number of samples to capture both of them if in our scenes have something like that. So subclasses of classes. So in that case, the number of training points should be diverse and large enough so we can capture that distribution. And this is very class dependent, landscape dependent. So it changes from case to case. And this is a big research questions that when we create our models, how much we can extend that model. So, and if you have, if we train our classifier based on training points we get from, or field data we get from Columbia Valley, can we extend and use that model somewhere else in southern BC? That's a big question, and that's is related to transferability of data spatially. So these are the questions that we don't have clear answer for that. But clear answer to me, when we make a model for area, we should make sure that we capture the entire distribution of each individual class. And with that, we are hopeful that that classification will be more accurate.
I guess I can add to that from a bit of like a, I guess, operational field data coordination perspective, and that my objective is to be able to give Amir the most clear data. And so to improve our like clarity of the information that we're collecting is important, and we'll be able to collect a lot of data using a more simplified method, because it'll just take less time to do, but we're also going to need a certain amount of data that has more detailed data. And so I think my mission is to figure out where we have known data sets and sort of what the quality of detail is within those data sets, and to figure out if that's enough. And if it is, then that's great. And then if it's not, then that would be where we would target our kind of next iteration of field work, and working with partners to do that. But it's important to be able to not go overboard and collect like so much detail that like you kind of have to pick the right thing for the right area. And so, yeah, I guess like determining the level of soil data required is a big question, and one that we don't really have a clear answer to right now, but that would be something that's sort of at the front of my mind to figure out.
Great, thanks, Robin. Or Aaron, sorry. I don't know where that came from. Neil asked a great question. I don't know if everyone's had a chance to see that one, or Neil, do you want to describe it yourself?
Sure. Thanks everyone for coming today and sharing your research. It's so exciting to see so many researchers doing work in BC on this topic. I know for a lot of our partners, including Ducks, Nature Conservancy, Canadian Wildlife Service, mapping products for BC wetlands has often been underfunded, and also we've lacked really good data for a lot of different management questions. So we're fortunate and really happy to be able to have crews support some of the field work this year. But I'm sort of wondering from your perspective, what would you see on the horizon in terms of improving these products? Where would you, if you were to receive, maybe limited resources, but you could do the next best thing, where would you put that funding, or where do you see the future of this going? And that was an open question to all of the presenters. So I'm wondering maybe, I'm not sure if there'll be time for each of them to answer. I'll let Kyla moderate that, but otherwise, if you want to put your responses in the chat as well, that might be a good spot too.
I think we have time. Unfortunately, like Deepa Philippi was unavailable this morning due to unforeseen circumstances. So I think we have until 12 at least. Maybe if everyone wants to give it less than a couple of minutes, we'll refrain it to that, but I think we have time.
Maybe I start because I think there's one important issue that I say first. When we were working on this scaling up the workflows, we noticed that the most important problem, all these discussions we discussed, the base for that is having reliable training points. I think having a platform that everyone can contribute to that, and we have wide distributed training points that are QC'd and then with the same standards, and then we can, and that should be put somewhere that is accessible to everyone. With that, then anyone in remote sensing community can come and contribute to that. There's tons of topics we can do research and improve these products, but I think the base for that is having reliable training points. That's the first step. Without that, we have to spend lots of time to have something really good to do a classification over a small area. But if we have that over entire BC, it's great. We can check the transferability of training points. We can check the quality of the products in terms of change detection. All that requires training points.
I can speak a little bit to the funding from Environment Canada. So the National Wetland Inventory project that I'm working on, and we work with the Amir on, as part of the Nature Smart Climate Solutions Fund. And so that's a $631 million fund that will be put out over 10 years to support projects that restore and enhance wetlands, peatlands, and grasslands with a focus on storing and capturing carbon. the thought is that there's 25% of Canada's wetlands that are high quality coverage. My personal opinion, like a few of us share, is it's probably not actually 25%, and the areas that have higher quality wetland mapping are probably in Eastern Canada. So there's definitely a data gap in BC with kind of how that feeds into it. And so, yeah, there's aspects of the National Wetland Inventory that includes some sort of a portal or an open database for field data, and then also for the predictive outputs that we have heard as a component of it, but I don't have any details on that right now because our folks in Ottawa are still figuring that out. And then obviously having higher quality field data is important. And so one of my next steps as sort of the BC wetland specialist for CWS is to delineate the areas of interest for the National Wetland Inventory that will kind of target our predictive mapping efforts on first, and then to see what we kind of have going there. I don't know if that fully answers the question, but the Nature Smart Climate Solutions Fund is sort of like what we're operating under. And then I know that Tina also referenced it. And so it's a pot of funds that's also available to a variety of partners and researchers as well.
Yeah, and I'd like to build on that a bit, Erin. So with all that funding that's available, it's really challenging for land users and various research groups to figure out where to start on restoring these wetlands, like which wetlands do we start with? And so I think that would be a good next step, is evaluating which wetlands we want to prioritize and throw money at and restore and enhance, that kind of thing. Because even right now, there's the city of Kelowna is talking about putting in wildlife corridors, and there's huge discussion around, okay, well, where do we start? And how do we secure land, and where and what areas? And so if we can feed in wetlands to those discussions, that's a really good point to make, to say, okay, this is a high quality wetland, let's start here. But figuring out how to move from just a wetland map into evaluating them is a next step that would take a lot of thought.
Yeah, so I will comment a bit more on the two data sets that are important for the wetland classification or the species classification. So the first is the remote sensing image. So as I mentioned, there are free but medium spatial resolution image and commercial high spatial resolution image. So maybe for specific wetland classes or specific species, the medium resolution, such as 10 meters, 20 meters, are good enough. But for some other wetland classes or species, so we definitely need high spatial resolution image. So therefore, I'm thinking maybe in the future for the wetland mapping or species mapping projects, we can consider to integrate them together. So for some, like say, areas, we use the free and medium resolution. And for some other areas, we use high spatial resolution image if we have the budget for that. So my second comment is about the field data collection. So as other speakers also mentioned, the field data is extremely important for the accuracy of the classification model. So I guess one potential solution, so not really a solution, but a potential way to do is using the UAVs to collect the training data, such as for some wetland classes or some species classes, we can fly the drones to take some photos and identify the specific classes of wetlands or species, not necessarily really have a group of people. So to go to the field and collect data, which is for sure more time consuming and costly. So I also understand, so we may need the soil profiles for the wetland classification. We also need, so we have to go to the field for differentiate different species. But I mean, so maybe for some specific classification projects, we can use the drone data as an alternative way. So not always have people to do the field survey, field ground truthing, but for some.
Thanks, Bing. Is there any other questions? I guess we'll just give a minute for anyone that may want to verbally say their questions. I don't see any more in the chat, but I hope that, thank you first of all to all the presenters that have both helped collaborate and contribute to while we are developing the protocol for what the wetlands workforce collected this year for predictive mapping data, for your help on that, as well as for sharing your ideas and thoughts and your current work. With this group, we've had a lot of questions throughout the field season, like what does this predictive mapping feed into, and higher level thinking. So I hope this gives people that have asked us those questions that Neil and I have done our best to answer, but we're not remote sensing experts, a better idea of what the goals and objectives and hopes for predictive mapping are going forward. And just a larger picture view, I guess, of what those points we make people tramp around and collect in homogeneous areas is working towards. But in respect with everybody's time, maybe I'll just pass it back to Alyssa.
Sure, thanks, Kyla. So I just wanted to direct everybody's attention to the chat. I just posted the link for the evaluation form. Once again, this evaluation will take about 5 minutes to complete. It's not very onerous, but it really helps us kind of evaluate the need and the desire of these types of webinar series to our funders in reporting, as well as in securing future funding opportunities. Thanks to our sponsors, we're able to host these events at no charge to all of our participants. So if you want to continue seeing really great webinar series that are free to you, please fill out the evaluation form. And then I guess if nobody has any more questions, so in terms of the recording, so we did record this session. We will be sending out a link to the recording. It usually takes up to a week to kind of finalize on our system. So hopefully by the end of the week, everybody that has registered for the event will get a copy of the recording that you can use for your references. And then in terms of individual questions for some of our guest speakers, I know that some of them did provide their contact information, but I'll check with Cindy to see if we can provide that in the wrap-up email as well.